So I haven't mentioned this next force too much yet. I might have talked about it, but it's called weight, and it's called a force due to gravity. So the force due to gravity equals weight, and it's another force. And what weight is weight is when mass gets exposed to a gravitational field. So the gravitational field will try to accelerate all mass towards the center of a planet. So weight is basically a force pulling mass towards center of planet. Okay. So no matter where we are on the Earth, if you're here, or if you're here, or if you're here, you see, no matter where you are on the Earth, when we're talking about being pulled towards the center of the planet, everybody's reference point would be the same, would always say down. So this would be the weight, and the way you usually typically draw the weight vector is you go to the center of the mass and you go down. So this is the center of the mass and going down, and this is the center of the mass and going down. They have weight which points towards the center of the Earth. So no matter where we are standing on the surface of the Earth, on the north hemisphere or the southern hemisphere, weight is pulling towards the center, and we all call that down. So in the formulas and stuff like that, so far we've seen small letter g is gravity. The formula for weight, so the formula for the force of gravity, and I typically use this shortcut, and I just say capital W for weight in this chapter, and it's going to be mass times gravity. So this thing right here is mass in kilograms, and this thing here is gravity. It's the magnitude of the acceleration of gravity on a planet. So when we're on Earth, basically no matter where you are on Earth, the acceleration is approximately 9.8 meters per second squared going down. So this is the acceleration due to gravity. Okay. And it's in units of meters per second squared. We will find out later on in chapter 5 that you get gravity based on a planet, and I can just jump to the ending result now, but the gravity on a particular planet equals some constant. This is a constant. It's a gravitational constant. You can look it up in the front of the book if you're interested now. Times the mass of the planet divided by the radius of the planet, and you have to square that, and you make sure everything's in the correct units. And we don't need this for right now, but there is a reason why the number for gravity is kind of unique to each planet. So when we talk about Earth, our gravitational acceleration is the number 9.81 meters per second squared going down. But that number is unique. It's not used if we're talking about going to our moon. It wouldn't be used if we went to one of the other planets, Mars or Mercury or whatever. It's just our number. So this will come up a little bit later, but there is a reason why, and Sir Isaac Newton figured out that. And I'll leave that for the time being. So here's another force. So we have many, many different types of forces. Here's another force. We call this thing here F sub n. That's a capital letter N, and we call it the normal force. Normal is a mathematical term that means perpendicular. Perpendicular means it's 90 degrees away from a surface. So a normal force is a perpendicular force that a surface will apply to some object. So with Newton's third law, I talked about action and reaction laws. So if I were to push on this wall, the wall will push back on my hand simultaneously with an equal and opposite force, and that will be action-reaction. But in this case, if I pushed on the wall, I'm pushing on the wall, let's say a force of 10 newtons into the wall. My hand's not moving into the wall, so something must be canceling out that 10 newtons of force pushing it into the wall, and that would be called a normal force. So, for instance, if this is the wall, and my hand right now is pushing into the wall, so this would be a force applied of 10 newtons, let's say. Well, if my hand doesn't push into the wall and through the wall, something has to be stopping it. And what can stop a 10 Newton force going to the right? A 10 Newton force which is going to the left. And that's what's called a normal force. There'd be a force here applied equal and opposite to the hand, and it would be a force normal of 10 newtons. Okay. If someone has a box and the box is sitting on the ground, so let's say we have this box, and let's say the box is 5 kilograms. So there's a couple of forces acting on it. Because we know the box isn't moving, it's not accelerating, every force has to be canceling out. So one of the forces would be the weight. If I went to the center of the box and draw a line down, we have this thing called weight, which is the mass times gravity. So the weight would be 5 kilograms times 9.8. And if you take a calculator out, you'll see that that comes out to be 49 newtons. Okay. Well, if it's not accelerating down, then every force is being canceled out. So what could cancel out a downward force of 49 newtons? An upward force. So the box is on the floor, pushing on the floor. The floor will push back on the box, equal and opposite forces. And so we would say right here, and it doesn't matter where you draw it. Some books will draw it going up to the floor. Some books will show the floor coming up like this. We'll say that's a force normal. And in this case, it equals 10 newtons going up. So if you look here, we have 10 newtons going up plus 10 newtons going... I'm sorry. Here's the force normal, so it's a 49 Newton force going up. So if you have a 49 Newton force going up plus a 49 Newton force going down, add those two vectors. Anything going up is positive, anything going down is negative. And when you do, they cancel out and you'll get 0. The net force on that box is 0. So this is called a normal force. You have to have direct contact with the surface, and when you do, the surface will push back perpendicular to the object. I'm sorry. The surface will push back perpendicular to the surface. If I was on a hill, and I had a child sledding on a hill, or a box is just sliding down the hill here. So in this particular case, it gets to be a little bit complicated. The box has a weight, and the weight goes straight to the center of the Earth, which is mass times gravity. I'm not going to work out the numbers here because we haven't learned about this yet. We learn about it soon. Well, if the box is pushing on the hill will be pushing perpendicular back on the box. So the hill pushes back like this. And this would be called the force normal. Okay? It's perpendicular. Now, it's not equal and opposite to the weight. The normal force does not have to be exactly equal and opposite to the weight. In fact, if you think about the winter time, what would happen if we put a sled on a hill that's a nice, smooth, icy, possibly hill? What would happen is they would accelerate down the hill. So you see, some of the forces would not be, all of the forces would not be canceled out. Some would be remaining. Here's a wonderful word problem. I don't have the word written out, but I gave the picture, and I'll talk about the situation. So we have this box, which is 70 kilograms, and someone is holding it, and so the person will be standing up here, and they're pulling on a rope. And so we're pulling on a rope with an applied force of 100 newtons, and this rope is being pulled at a 50-degree angle above the horizontal. And the questions would be multiple. You could ask these type of questions. First of all, let me say, we're not talking about friction yet. That comes near the end of this chapter. So we're saying find these things. Find the weight of this box. Find the normal force on this box. Find the net force acting on the box. And then find the acceleration acting on the box. So all the weight, the weight is just a formula. So what I would do is I would go towards the center of the box. And right from the center, I would draw a line straight down. And I would say weight equals the mass times gravity. So in this case, the weight equals 70 kilograms times 9.8. And that comes out to be 686 newtons. Okay. So that's one thing. We've got that done. That's the true weight. I would also say that we should never ever work with forces that are going between the x and y components. So I would say take this force and break it down into an x piece and a y piece. So I have the hypotenuse of 100 and I have the angle of a 50. So the force going in the x direction would be the hypotenuse, 100 newtons, times the cosine of 50. And if I plug those into my calculator, I get 64.3. And if I do the same over here, the vertical piece, F in the y direction, would be 100 newtons times the sine of 50 degrees. And that is going to come out to be 76.6. Okay. What I might do is I might redraw this. We talked in the last section about the free body diagrams. Well, if I were to draw the free body diagram, a free body diagram has all the forces acting on it. So there's one force, the weight. Here's another force, this applied force. There's a third force on this thing that's acting on it. It's the normal force. So there's a force from the ground pushing up. So we have this force normal. And we don't know what that one is, and that's tricky for a lot of students. Many students think that that force normal is going to be the equal and opposite to the weight, but it's not. You know, sometimes it is and sometimes it's not. So what I'd like to do is redraw this and come up with a simpler version of the free body diagram. So what I'll do is I'll draw the ground. I'll draw the box. I'll say it's 70 kilograms. I'll say that we have this weight going down, which is 686 newtons. I'll say we have this force pulling the box to the right with 64.3 newtons. I'll say we have some of this force is actually trying to pull the box up off the ground. So that force going up off the ground is 76.6 newtons. And we also have this thing called a normal force. So the normal force is over here someplace. And we want to know what the normal force would be. Well, if you only look at the vertical forces, the normal force is going to be such that all the vertical forces are going to cancel out. Because as you pull this box across the ground to the right, it's not going to elevate up into the air. It's not going to sink down vertically into the ground. It's just going to go to the right. So the normal force would be the difference between these two here. Okay? And if you take a calculator and you subtract these two, take 686 and subtract 76.6, the normal force, which is 609.4. And you can check. You have 609.4 and you add it with 76.6. Both of those are going up, and they will equal the total force going down of 686 newtons going down. Okay. So because of that, what just happens, all of the vertical forces cancel out. So these forces are no longer here. They've all canceled out. Okay. And if they've canceled out, we don't even need to show them. So I could technically erase all of those different forces. And right now, we have just done this. We have said we found the normal force. So that's done. Okay, when you cancel out all the forces that no longer exist, so I'm going to erase this, and I'm going to erase these ones up here. The only force that's left is what's called the net force. So this thing right here is the net force. So that is the sum of all the forces. 64.3 newtons going to the right. Okay. How would I get the acceleration? The acceleration is going to equal the sum of all the forces over m. So it's going to equal 64.3 newtons over m, which is 70 kilograms, which is equal to 0.92. So the acceleration is equal to 0.92, and if someone grabbed this box and tried to pull it with an applied force on a string of 100 newtons at this angle, and we're saying there's no friction in this particular case, then all of these things have been found. We found the weight was 686, we found the normal force I just erased it a moment ago. We found the net force. It's right here, 64.3, and we found the acceleration of 0.92 meters per second squared. So all of those things were found. Here is a quick problem where they have shown us a picture and they said we have a box that's 45 kilograms and it's attached to a cable, and the cable is going to lift this box up and pull it up into the air, and the tension in this cable is 500 newtons. And the question is, find the acceleration on the system, find the acceleration on the box. So at first glance, this looks like a very easy problem, a very quick problem. At first glance, it may look like you just have to do F equals ma, because they've given you the m, the mass, and some people think they've given you the net force, but they haven't. So what you always have to do is you have to make sure you draw the free body diagram. The free body diagram shows every force that's acting on the object. So the one force we don't see is the weight. So the weight is mass times gravity. So we have to calculate the weight. So it's 45 kilograms times 9.8. If I do that, the weight comes out to be 441 newtons. Okay. So these are two real forces. The net force is not a unique real force. The net force is the sum of all the forces. Okay, so this is a real force applied to the box. It's called the tension in the string or the rope or the chain. This is a real force acting on the box. It's called the weight. And they're doing opposite things right now. So if I tried to find the net force, I would say the sum of all the forces, well, what are they? I'll add up these two force vectors. If it's up, it's positive. So I'll say plus 500 newtons. And I'm going to add them because this symbol right here, sigma, means add everything up. So I'm going to say plus 500, and I'm going to add a negative 441. Because that's what you do when you add vectors. You have to add them together. Even if it's a negative vector, we're adding a negative vector. When I plug that into my calculator, the sum of all the forces comes out to be negative 59. Positive 59 newtons. So a positive 59 newtons means that the net force on this particular box is upward. So if I had to redraw that, I could say, we always want to simplify our free body diagram. So with one picture, I could say we have 45 kilograms, and the net force on this box is 59 newtons. That's my simplified free body diagram. So how could I get the acceleration based on this? Well, I could say the acceleration is equal to the sum of all the forces over m. So it's going to be 59 newtons divided by the mass, which is 45 kilograms. So the acceleration rate is 1.311 meters per second squared. And that's the rate at which this box is going, accelerating up into the air, which is a much different answer than if you didn't even think of this gravity force, the gravitational force here. If you only saw the tension as being the net force, and this as being the total mass, you would have had a completely different answer. But that's the answer. The acceleration is a positive 1.311 meters per second squared. A lot of physics problems ask something about the apparent weight. How heavy does the person feel that they weigh? And your apparent weight is not the exact same as your true weight. Your true weight never changes. So the true weight goes from the center of your being, and you draw a line straight down, and this would be your true weight, which is just your mass times the gravity. But the apparent weight is equal to the normal force. So force normal is the same thing as your apparent weight. Okay. And so what do I mean by that even? if you were to stand on the scale at your house, and you don't move, if you freeze your body and don't move, you're not accelerating. So if you're not accelerating, every single force has to cancel out. So the true weight going down would have to be equal and opposite to a force going up. And in that particular case, your true weight would be the exact same as your normal force. And so the scale actually is giving you a reading of the normal force. But what if you tried to accelerate your body up or down? Well, if you just took your body and accelerated it down, and you're doing like a squat thrust or something to that effect, as you accelerate down, you'll notice that the scale reading seems to be a little bit lower. And if you accelerate up, so you must have been in the squat position and you accelerate up, then you'll notice that the reading on the scale seems to be a little bit higher than your typical weight. So here's two forces acting on a body. If these two forces are equal and opposite, the body's not accelerating. If one of the forces is bigger, if this force here, the upward force, is bigger, that actually means that the body's accelerating upward. And if this force here is bigger, then that means the body would be accelerating downward. And that's kind of easy to understand if you're talking about a tug of war and two people are holding a rope with a knot in the middle, and you would say, yes, I'm looking at a top view of a tug of war. If one side is pulling harder, I understand how the knot would accelerate in that direction. But these aren't physical forces that you can see. You know, you can't see the force of your weight pulling you down to the center of the earth, and you can't usually see the normal force pushing against you. But they still do exist. And the typical thing that they may do with a problem like this is to put a scale into a moving elevator. And if they put the scale into the moving elevator, and we tell us some of the numbers, then we would know what the rate of acceleration would be for that particular person in the elevator. And if we know how the person is accelerating, then we know how the elevator is accelerating, and we would be able to figure out how the tensions are changing in the cable that's holding the elevator up. So there's a lot of applications to this, not just talking about putting a person in an elevator. So a situation may be like this. We have an elevator box. Okay. Somebody has put a scale into the elevator box, and this elevator is attached to a cable which is pulling it up. But we're not even going to look at that. Okay, so we're in an elevator. And what's happening is we could be told we would be told possibly that this person has a mass. So let's say this person has a mass, and their mass is 50 kilograms. Okay, and we could say that at this particular moment the elevator is accelerating upward, and we could say the acceleration rate is 1.5 meters per second squared. And we could say, find the apparent weight on this particular person. So that would be our word problem. That would be our question. So what we would do is we would draw the free body diagram. The free body diagram is actually my person. So my person, I don't have to draw a person. That's the object right there. That's the person. That's 50 kilograms. Then I could say that this mass has a weight. So the weight, the true weight, is mass times gravity. So the true weight is going to be 50 kilograms times 9.8. So that comes out to be 49 newtons. I can also say that the acceleration here would be giving me the net force. So I know the net force automatically. The net force is going to be mass times acceleration. So the net force is going to be 50 times 1.5, which equals 75 newtons. Okay. So I have a net force on this, but the net force is not the true force. The net force is not the real force. a real individual force acting on it. The weight's acting on it, and so isn't the normal force. So the normal force is basically pulling it up. So the force normal is unknown at this moment, and that's what I'm looking for. So how would I find the normal force? Well, when you find out what the net force is actually the sum of all the forces. So I'm trying to see if I take this force and I add it to this weight force, what will I get? I'm sorry, I just noticed I made a mistake here. 5 times 9.8 is 49. 50 times 9.8 is 490. So this is a mistake. That number should be 490 newtons. We all make mistakes occasionally. So how would I go about getting this number right here? Well, what I could do is I could apply a formula to it. And the formula I could apply to it would be the sum of all the forces. Now, what does the sum of all the forces technically mean? It means add up all the forces. So over here, I have a force going in the upward direction. So I will say plus force normal. I'm going to add more because sigma means sum of, add up. So I'm going to add the other force, which is the weight, but it's pointing down. So I'm going to say add a negative weight. And that's it. So I know what the sum of all the forces is because I did it over here. The sum of all the forces is a positive 75 newtons. And that equals, and the normal force is unknown. And the weight is this number, negative 490. So I just want to solve this equation. So how do I get force normal by itself? Well, I'll add 490 to both sides. So that's gone. And when I do this piece over here, I will get 490 plus 75. This is a positive 565 newtons. So what I've just done is I have found what the apparent weight is. This is how heavy a person would feel if they were experiencing an upward acceleration on an amusement park ride. Usually an elevator does not have an acceleration like this. An acceleration in an elevator would be a small decimal point number, so you will barely feel like the elevator is accelerating up or not. But if you were in an amusement park ride and they accelerate you up at this rate, then what you're going to feel is your body's going to feel heavier for those moments that you're accelerating up. And so a person who usually weighs 490 newtons will feel like they weigh more. 565 newtons. In physics, we typically talk about problems where there's a car accelerating or there's a car going at a constant speed. In this chapter 4, we're talking about Newton's laws. Very frequently, we talk about equilibrium problems. So an equilibrium problem is dealing when every single force ends up canceling out. So by definition, equilibrium means the sum of all the forces is going to equal 0 newtons. I left a space there so you could see it's not the word on, it's 0 newtons. So that means all the forces going to the right will equal all the forces going to the left. That also means all the forces going up will equal all the forces going down. So what that means is the sum of all the forces, if I talk just about one dimension, all the forces going up have to equal an opposite be opposite to all the forces going down, and all the forces pulling to the left will be equal and opposite to all the forces summed up pulling to the right. And when that happens, everything cancels, and we have equilibrium. So if I give you a problem with equilibrium, it looks like this possibly. So here what I'm showing is a flower basket that has a mass of 3 kilograms, and it's being supported by two different strings, two different ropes. So ropes can pull, they cannot push. So the rope to the left is pulling on this knot going to the left, and I'll call that force of tension 1. And the rope over here is pulling upward and to the right, and I'll call that force of tension 2. And there's one right here where the basket is attached, and I'll call that the force of tension 3. And the sum of all of those three forces have to cancel out, because as we can see, the basket is not accelerating at all. So the way we do that is we basically have to look around, and if you can notice, this string over here is pointing in two directions. This string is pointing towards the right, and this string is pointing up to the top of the board. So you see, if I take this component piece here, instead of talking about this string right here, I can talk about the force sub t of 2 in the x direction, and I can talk about this as the force sub t 2 in the y direction. And I'm capable of finding out what those things are. So instead of talking about the force subscript 2 in this line, I'm going to take these other two pieces. And you see, what is this one right here? The one pulling the string, the knot straight up, that's force subtension 2 in the y direction. So this is force tension 2 in the y direction. Okay. Are there any forces that I can find outright right away? And there is. This thing has a mass, and so you see mass will have a weight. So there is going to be a weight here going straight down. So weight will equal the mass, 3 kilograms, times gravity, which is 9.8, which comes out to be 29.4. So 29.4 newtons is the force going down. So this particular knot has a force pulling it straight down of 29.4 newtons. If that's the case, there must be a force here pulling this thing straight up. So we have a force pulling this thing straight up with the same number, 29.4. So this one right here is 29.4 newtons. Okay. Let me erase. So I've just found that the vertical force right here is going up with a force of 29.4 newtons. But there is no physical vertical force on this knot going up. What there is a force going to the right. So if I look at this knot, there's a force going this way. And this was 37 degrees. And I said that that was broken up into two pieces. It's going to the right, and I call that force of tension subscript 2 in the x direction, and there was a piece going up, and I call that force of tension subscript 2 in the y direction. This is the piece right here that equals 29.4 newtons. So you see, what I have is I have a triangle, and I have the angle, and I have the opposite leg. So if you know that, there's a formula using sine and cosine and tangent where we can find some of the other pieces. The way I do it is I usually define the opposite leg as being the hypotenuse times the sine of the angle. So I know the opposite leg is 29.4 newtons, and I don't know the hypotenuse, but I do know the angle is 37 degrees. And so if I go and I try to solve that, and I'll try to write a little bit not so crooked, I will say the hypotenuse is equal to 29.4 newtons divided by the sine of 37 degrees. And the hypotenuse will come out to be, in this case, 48.8 newtons. So this thing comes out to be 48.8 newtons. So that's this one. That's the real tension. I called this originally the force of tension subscript 2. So it's 48.8 newtons. Well, what else can I find? Well, you see, I have a triangle and I have two pieces. I have the hypotenuse and I have the opposite leg from the angle. So I can find the adjacent side. I can either use the Pythagorean theorem, a squared plus b squared equals c squared, or I could say this side right here, which is adjacent to the angle, I could say the adjacent side is equal to the hypotenuse, 48.8 newtons, times the cosine of 37 degrees. So if I plug that in, the adjacent side comes out to be 39 newtons. So we have this here as 39 newtons. So I can go back over here and I can tell you this rope pulling the knot to the right is 39 newtons. And then that must mean that the rope pulling the knot to the left is 39 newtons. Because everything has to cancel out. So I have some forces going to the right, and I have some forces going to the left. They're equal and opposite. I have a force going up, which is 29.4, equals a force going down, which is 29.4. Equal and opposite. But in real life, I don't have these forces here in yellow. In real life, I just have this one force going up along the line here. And if I did the Pythagorean theorem with a base of 39 newtons and a height of 29.4 newtons, and I did the Pythagorean theorem, the hypotenuse would be 48.8 newtons. So, for this last piece, I'll have to erase a little of it here. I would say that I have a rope going this way, and the tension of the force of the tension 2 came out to be 48.8 newtons. And that's a typical question. Find the tension in those two different ropes. So I should have actually started off that way. So that would have been a problem, and the question should have been find the tension in the two ropes. So the tension in the left-hand rope that's horizontal is 39 newtons, and the tension in the right-hand rope, which is going up at an angle, is 48.8 newtons.